We're going to do a little bit on the end of 10.4 that we didn't finish up last time. Can somebody confirm that this is where I left off? We set up example 3, we didn't finish it, is that true? Maybe it didn't look exactly like that, I just want to know if that's where we left off.
Yeah.
We set it up,
We set it up and we got to like,
can we go further than that maybe?
no, that's exactly what we
That's
said.
about where we stopped, okay, that's where I thought we were. So the plan is to finish example 3, and then there's one more little topic in 10.4 on finding lengths in polar coordinates, and that's the end of chapter 10. Then a week from today, we're going to review for the test on chapters 8 through 10. And then the next Tuesday after that, we're going to take the exam on those chapters. So the second part of today, probably about a half hour or so, maybe up there, right, is 11.1, which is the beginning of sequences and series, which is all what chapter 11 is about. Chapter 11 is a really long chapter. I don't know if you looked, but we're doing chapter 11 for 1, 2, 3, 4, like 5 weeks. That's all we're doing is chapter 11, so it's on and on and on. Luckily, it's all kind of tied together though. So we're going to start doing that today. We'll do some of that again on Tuesday, and then we'll review them. Good? Okay, so we have set up example 3. I'm sorry?
I thought it was from -5 or 6 to 5 or 2.
Yeah.
Well, did I not set it up with symmetry?
Well, yeah, I know, but I thought the symmetrical thing was from -5 or 6 to 5 or 2. It was like that.
Oh, was it?
Yeah.
I understand. I thought you said -5/6 to 5/6. You're right. I went off my memory. Tell me again. -5/6
to
5/2. I remember that now. Sorry. We set it up before and I went off my memory without looking at the picture. It's a good thing he's still awake. That's where we left off with the correct bounds now? The hardest part of these is setting them up. We did that last time. Now what? Yeah, distribute, multiply everything out. It's going to be very similar to what happened last time. So we'll keep the bounds here. When I multiply this out, that will be 9 plus 12 sine theta plus 4 sine squared theta minus 4 from that 2 squared. And it's very faint. Trying to squeeze it. So these first 3 terms are just for multiplying that out. Good there? So if we combine like terms, well, this is much better. -π/6 to π/2, that's just going to be 5 plus 12 sine theta plus 4 sine squared theta d theta. So this is similar to what we did before. What do we need to do to this before we can keep going? I can't quite integrate it the way it looks.
Gotta get rid of these 4 sine squared theta.
Yeah, the sine squared, we don't have a way to integrate sine squared. So once again, we need that identity, which I will always give you these on an exam because they show up all the time. The reduction formulas for reducing sine squares is another one for cosine squared. So we're going to use that to replace our 4 sine squared theta. So this term right here is going to get replaced with 4 times 1/2 times 1 minus cosine 2 theta. Just this term. See that? So then, -π/6 to π/2. This will be 5 plus 12 sine theta plus, this is a 2. I'm going to distribute it through there. So it'll be 2 minus 2 cosine theta. 2 theta. Just simplifying so we can get to the integration part. And then I'm going to combine the 5 and the 2. So -π/6 to π/2 7 plus 12 sine theta minus 2 cosine 2 theta, d theta. Now we can integrate. Hopefully. Integral of 7, 7 theta. Integral of 12 sine theta, negative 12 cosine theta, right, because we're integrating. Negative 12 cosine theta. Minus the integral of cosine 2 theta is sine 2 theta over 2, which is going to reduce with this guy. So we just have a sine 2 theta. Right, so there was a 2 out here and we're divided by 2. Reverse chain rule. If you're not sure, take the derivative of this and see if you get that. That's the easiest way to do it. Derivative of this would be cosine 2 theta times the derivative of the inside. There it is. And then we need to evaluate all of that between negative pi over 6 and pi over 2. We can handle that. So that will equal 7 pi over 2 minus 12 cosine of pi over 2 minus sine of 2 times pi over 2, which is pi, minus negative 7 pi over 6. Plug this in there. Minus 12 cosine of negative pi over 6 minus sine of what? What happens when I plug negative pi over 6 in here?
0 sine.
Nope, it's not
Sine
0.
pi.
Pi over 3, right? Because it's 2 pi over 6? Well, negative 2 pi over 6, so I'll make it negative pi over 3. Doubling that angle. What's cosine of pi over 2? 0. This one is 0. Sine of pi? 0. This is exactly why we do the changing the bounds and use symmetry, because you plug pi over 2 in here and things just go away. Otherwise, you would have been carrying around all these pi over 6s forever. So those are 0. So I'm going to start recopying what I have here then. I have 7 pi over 2 minus negative 7 pi over 6 minus 12. Need the cosine of negative pi over 6. Cosine is positive in the first quadrant and in the fourth quadrant. So it's really the same as cosine pi over 6. If you don't know though, you can always draw a picture. Negative pi over 6 is down here. Relationship is here. That's positive, this is negative because it's going down, right? What's the cosine of that? Root 3 over 2. 12 times root 3 over 2 minus the sine of negative pi over 3. Pi over 3 is down here. So the sine of that is negative root 3 over 2. Negative this time. Minus negative root 3 over 2. We love our trig. We love our trig. Keep saying that. Someday you'll believe it. 7 pi over 2 plus 7 pi over 6 plus 6 root 3. I'm distributing this negative through here. What's here? That's 6 root 3. And this is plus, oh, it's minus. Careful here. I've got a minus, and a negative, which I almost lost up there. So it's negative root 3 over 2. My last step's gonna be to get a common denominator. This is 21 pi over 6 plus 7 pi over 6. And I'll get a common denominator for these guys, 12 root 3 over 2 minus root 3 over 2. So I wrote these with a common denominator. I wrote these with a common denominator. 28 pi over 6 plus 11 root 3 over 2. And this guy will reduce. The final answer is 14 pi over 3 plus 11 root 3 over 2. That is the total area in between the one curve and inside the one and outside the other. I can't remember the exact question
It
is.
was like a circle radius 288.
Yeah, but does someone look like Toad? Is that the one?
Yeah.
I'll never forget that. Questions? Notice how long this problem is. We set it up days ago. Setting it up takes a long time. Evaluating it takes a long time. And there's lots and lots of places to make mistakes. On the exam, I'm not going to have you evaluate every single one of those because there's just not enough time. You'll be setting up a few and there'll be a couple that you'll be asked to evaluate. Most of the ones I ask you to evaluate on an exam are not too long and too messy just because of the time crunch. Questions there? We can handle it. Okay, on the next page is how to find arc length in polar coordinates. So I'm on page 107 of our notes. Can I erase this? You guys got all this? Yeah? Sure? So there's an arc length formula for how you find the length of a curve if it's given to you in polar coordinates. We have the arc length formula already for Cartesian. We did that last time. Not last class, but last exam. But the arc length formula is kind of similar. A little bit different. Anybody remember what the arc length formula looked like in Cartesian? Kind of close to this.
Square root of 1 plus the derivative.
Yeah, it had 1 plus the derivative squared in here when we were doing arc length before. Now it's an r squared. And it has to do with the same thing with our, remember our formulas for areas have that extra r squared in it. It all has to do with how the relationship between x's and y's. They're similar, but a little bit of tweaks. You don't have to memorize it, you just need to know how to use it. So the questions are just going to be find the length of this curve. This is the formula you'll need to find the length of the curve. The first example I have here is r equals 5 to the theta. Let's make this curve. 5 to the theta from 0 to 2 pi. What kind of curve is that?
Circle.
A circle? If it was r equals 5, it'd be a circle, a radius 5. A half circle?
Like half an A almost.
Let's just kind of make a little table to think about what's happening here. What happens when theta equals 0?
There was one.
All right, come on. When theta gets to say pi over 2, pi over 2 is 3.14 divided by 2 is like 1.5-ish. 5 raised to the 1 point something. What is that, roughly? If you have a calculator, you can tell me too. 5 to the 1 is 5. What's 5 squared? 5 to the 1 is 5. 5 squared is 25. This exponent is somewhere between 1 and 2. So what do you think this is?
About 12.53.
Did you put in your calculator? Just put roughly something between 5 and 25, so let's call it 12.5. We're approximating, approximately. By the time I get to pi, pi is a little bit more than 3. Well, what's 5 cubed? 125, right? So when I get to pi, it's gonna be something slightly bigger than 125? You got that, Jose, too?
156.
156?
Yeah.
Makes sense, a little bit bigger than 5 cubed. What's happening to my r as theta increases? Ooh, someone just said it, I heard it really faint. It's just increasing, it just keeps getting bigger.
Is this fine?
Because it's getting exponentially larger. What is it by the time I get to 2 pi? It's probably a bunch of digits.
24,646.
24646?
Yes.
These are all approximations, mind you. So if I wanted to graph this, okay, number one, my scale would have to go out to 24,646. That's a problem. But I'm going to kind of fudge my scale to give you an idea of what it looks like. The picture of it says it starts here at 1. Here's 1. By the time I get to pi over 2, I'm out, let's call that 12.5. I'm out here, right? By the time I get to pi, I'm all the way out here at 156. By the time I get down here, I'm going to be even further out, and by the time I get over here, I'm all the way out to 24,000. My scale's way off. It's actually a spiral, you're right. It just keeps spiraling out, and you keep rotating around, getting further and further away. So it's actually a spiral. So the question is, how long is this piece if I went all the way from here to there? That's the question. What is the length of that curve? Knowing that we stop roughly 25,000 out there, roughly 25,000 out here, I expect the length of this curve to be pretty long, because just this distance is 25,000, almost. Everyone okay with what we're looking at? Okay, so let's talk about how to find the arc length then. That was just a picture, so we knew what we were working with. What should I do? Take the derivative, so I need to plug it in there. Well, there's a review question. What's the derivative of 5 to the theta?
5 to the theta.
Times something else.
Would be,
It's not 1. The chain rule thing. It's actually times the natural log of 5. You learned back in Calc 1 before you met me that the derivative of any a to the x is a to the x times the natural log of a. You can use implicit differentiation to show you why. The reason the derivative of e to the x is just e to the x is the natural log of e happens to be 1. But if it's anything other than e, you have to multiply by that natural log of 5. A review question for you. Okay, so let's set up our arc length formula. So the arc length, in this case, we're going from 0 to 2 pi. It was given to us. We want the square root of r squared, 5 to the theta squared, plus, here's my derivative, 5 to the theta natural log of 5 squared, d theta. So I plugged in my r. I plugged in my dr d theta, the derivative. Okay there, what I put in there? Messy, I know, but we can handle it. What's a nicer way to write 5 to the theta, the quantity squared? Is there a nicer way to write that? Use your algebra. What are your rules for exponents? You just multiply them, right? Because we raised the one exponent then the other one. So if I multiply those exponents, I can write that first term as what? 5 to the 2 theta. Much nicer. So I have the square root of 5 to the 2 theta. Plus, the same thing happens here, but the natural log of 5 also gets squared. 5 to the 2 theta, natural log of 5 is also squared. Can we simplify that at all? Guys over here saying,
Factor out 5 to the 2 theta.
We could factor out a 5 to the 2 theta. It's in both terms. Might as well factor it out. Oops, I got my bounds, sorry. 0 to 2 pi. So if I factor that out, 5 to the 2 theta, I'm left with 1 plus natural log of 5 squared. Right, if we factor out the 5 to the 2 theta. But notice the 5 to the 2 theta is under the square root. Can I pull it out of the square root?
Yep.
Yeah, what will it be?
I think
5 to the theta, that's exactly what happened to it, right? 5 to the theta squared, if you take the square root of it, take half the exponent, that's going to come all the way out. So now I have 5 to the theta times the square root of 1 plus the natural log of 5 squared d theta. Okay, we took the square root all the way, the 5 to theta all the way out of the square root. It was a perfect square. Now, this looks pretty messy, but it's not. Why are you saying back there, Joseph?
Because effectively it's just the the square root of 1 plus the square root of ln, ln of 5 squared, which would just be 1 plus ln of 5 times 5 theta.
Well, we can't take the square root of it because of the plus sign in there.
it's just a constant.
But the cool thing is it's really just a constant. That's just some number that you can put into your calculator, right? 1 plus natural log, it's just a constant. So if it's a constant, we can just pull it all the way out front. It's a messy constant, I'll give you that, but it's just a constant. It's not, we don't have to integrate it. There are no thetas in there whatsoever. So I'm going to pull that all the way out front. And then I'm going to integrate what's left, which is just 5 to the theta d theta. Now, I reminded you how to take the derivative of it over here. So what do you think is going to be different when we integrate it? Instead of multiplying by ln 5, we're going to divide by ln 5. That's the only thing that's different, right? Chain rule in reverse. So I have this square root up here still, times 5 to the theta over ln of 5. And I have to evaluate that from 0 to 2 pi. All of this is a constant. That's all just a messy constant. So I'm going to hang on to that. I'm going to put it all together. And then I'm going to evaluate what's left. 5 to the 2 theta minus 5 to the 0. Oh, 2 pi. I put 2 theta. 2 pi. Okay? There's only one more thing I can simplify here. What is it?
5 to the 0.
5 to the 0 is just 1. So there's not much more we can do, it's just a messy answer. So I have the square root of 1 plus ln 5 squared times 5 to the 2 pi minus 1 all over the natural log of 5. And that's your answer. That's your exact answer. Now, the question I have for you is who can carefully plug that into their calculator and see what it equals? Plug it in accurately and carefully. See what we parentheses right. Reason I wanna know what it is a decimal is I want it to match this picture over here, because it has a horrible scale. This beautiful spiral that went out to there,
It's 29,000.
29,000 and some change.
29,015.56.
So based on the points that we found over here, that makes sense to me. Because this distance right here was roughly 24.6 thousand. We've got that distance stretched out a little bit more because it curves down, and then these are all really short compared to those. So it makes sense that this whole length. If you tried to graph it on your calculator, it'd actually be really hard to see even because you can't get your window such to fit everything. If you did, it would be really tight and then go zoom way out there. So almost all of it actually is stretched out on the bottom there. So it makes sense. If the answer was 18, I'd be a little worried. Questions on that one? This one was messy because I gave you a function that wasn't so fun to work with, but those functions happen. So I actually have another example of this that I'm tacking on here because I only gave you one. And there are some in your lab and on your homework where they don't give you bounds. So the question is, what do we do with that? So hopefully you left some room there. If not, I think there's room on the back. So this one was example 4. If I wrote it down, this was example 4. We're adding an example 5. It's not in your notes. But it's actually quicker than that. Just to make sure we've got it. So I'll add this one into your notes. Example 5. Find the length of R equals 5 sine theta. That's all you have. The whole thing. Did you write that in there? What should I do first? We need the derivative to plug into our arc length formula. So we can do that. What's drd theta? 5 cosine theta. Okay, we got that. So looking at my formula over here, I have R. I have drd theta. What don't I have? I don't have any bounds. How long, does it go on forever? Right, find the length of the curve. Like that one, we knew where to stop. That one technically went on forever too. If I kept going, I just keep going around and around and around. So they told me where to stop there. How do I know what the bounds are?
Can you do symmetry and do 0 to pi over 2?
Yeah, we could maybe do some symmetry and do 0 to pi over 2. So you must be looking at something to come up with that.
Graph.
Ah, so he's looking at a graph. So let's maybe look at a graph of R equals 5 sine theta. Maybe you remember what that looks like based on what we've been seeing. I like to just plug in what happens on these bounds, on these axes here to see what happens quickly. When I plug 0 in there, I'm at 0. By the time I get to pi over 2, 5 times sine of pi over 2, that's just sine of pi over 2 is 1. So I'm up here at 5. And then by the time I get back to pi, I'm back at 0 again. If you've done some points in between, basically you do this. That's the whole thing. Now I said it. What did it take for me to graph that whole thing? Where did I start and where did I stop? Started at 0. When I got to pi, I was already back down here. So this wasn't given to us, but if theta is between 0 and pi, I get that entire graph. A lot of people will automatically put in 0 and 2 pi because that you think of that as one full revolution. I'm backwards from you, sorry. One full revolution. But if I did 0 to 2 pi on here, I would graph that whole thing twice. It would go around twice. One thing I do recommend if you're using your calculator is to go in and change your window so that you make sure you only get the picture one time. Like change it enough to cut off part of it so you know that's not enough, whatever it might be. Because you can't tell. If you graph it from 0 to 2 pi, it's going to look the same. But it actually is drawing it twice, which would be double the length of that curve. So 0 to pi would be one way to set it up, but what Carla said is we could use symmetry and just go 0 to pi over 2 and then double it. Either way. In this case, I don't know if it would make much of a difference because evaluating trig at pi and at 0, or at pi over 2 are not much different. And there's not any fractions we need to clear, but it's not wrong. So you can use the symmetry. So I'm going to start with the 0 to pi. Everyone okay on why it's 0 to pi? You're saying no back there, Tiger? I'm not sure. Quick. So if it's 0, I'm at 0, so that's the starting point. By the time I get to pi over 2, I'm up there at 5. So 0 to pi over 2 graphs this piece right here. By the time I get back to pi again, I'm already back at 0. So I just went 0 to pi over 2, back to pi, and I've drawn that whole circle only once. So if I kept going, like to 2 pi, I would go 0 to pi, draws the circle once, and then another one would draw it again. And so I only want to go around the circle one time. And that's what I was talking about. If you're not sure, go in and adjust your window, your starting and stopping theta in your calculator, and make sure that you're just getting one part of the graph. And I always back it up sometimes if I'm not sure the graph's getting sloppy, to see if how I can just get half of it maybe. So if you had done 0 to pi over 2, you would have gotten half of this circle. And that would have said, okay, double that. You can play around it a little bit. It's not always 0 to 2 pi. It's exactly why I put this example on here. Okay, so then I want r squared. That's 25 sine squared theta. Plus the derivative squared. 25 cosine squared theta. He recognizes the identity in there after we factor out that 25. I'm going to write it down so you see it. 25 times sine squared plus cosine squared. You recognize this identity? That's just 1. So that's just the square root of 25. This whole thing reduces to 5 d theta. What's the integral of 5? 5 theta, right? 5 theta evaluated from 0 to pi, 5 pi minus 0, that's 5 pi. That's the distance around this circle. What's another way to talk about the distance around the circle that you learned before you ever learned calculus? Distance around the circle? There's a name for it.
Circumference?
Circumference. Because it's a circle, the circumference is the distance around the circle. Who remembers the formula for the circumference? 2 pi r. Because this equation was a circle, we could have found the length of the curve this way. What's the radius of this circle? Well, the radius. The radius of this circle. This distance right here is the radius. What'd you say? 2.5? Half of 5, right? 5 over 2. 2 pi times 2.5. Hey, what do you know? 5 pi. The circumference is the circumference. Now, it only works if it's a circle to take the shortcut, obviously. If it's not a circle, though, you're going to set up an integral. We couldn't have done that for the spiral over there. All right, let's talk about chapter 10, because we're wrapping that up. Chapter 10 had a lot in it. Chapter 10 started with parametric equations. Jogging your memory because spring break wiped everybody's out somehow. Parametric equations, what are those? What does that mean? Parametric equations, what do they look like?
When you have t's.
Yeah, there's like a t, there's a third variable. Actually, some of them had thetas even in there. But you have a t. X is defined in terms of t, y is defined in terms of t. We can graph things in parametric, we can eliminate the parameter to get a Cartesian, we could find slopes and tangent lines. So there was also including calculus. So that was actually 2 sections. The first section just introduced the parametric equations, and the second section actually had us doing equations of tangent lines and where there were horizontal tangents or vertical tangents. So that was chapter 10. And the second part of chapter 10 was polar. And then the calculus with that. Where we did tangent lines, we did areas between curves, we did arc length. So chapter 10 only has these 2 short ideas in it, but there's a lot in there. So that was chapter 10, because our test is on chapters 8, 9, and 10. 9 was all those differential equations we did. That's a while ago. Where you did slope fields, we did separable differential equations. 8, 9, and 10. And 8 we just did the one section, I think that was when we started arc length. I think that was arc length. I have to go back and look. So when we talk next week and do that review, it's been a while, and spring break, like I said, wiped everybody's brains out, so we need to put it back in there. It can all be replaced, we're good. So before we start chapter 11, I think we'll go ahead and take our break now, just because I don't want to start it for 5 minutes and then take a break. So let's go ahead and take a break now, we'll come back in 10 minutes, and then we'll get going with chapter 11.